So then, in the last video, we looked at the static equilibrium of a body, and we looked that there was a general case of that all the forces must balance, so all the forces must have a net resultant of 0, and that we could split these down into the vector force equations in the x direction, y direction, and z direction to get orthogonal equations of static equilibrium, so that we had sum of the forces in the x direction equal to 0, forces in the y direction sum equals 0, and the sum of the forces in the z direction equal to 0. In addition to the forces giving rise to displacements, which we've shown in green on the body diagram there, a situation can arise where if we have the same body and that's subjected to a system of forces which have a couple, so forces, two equal and opposite forces separated by some distance, that gives a twist, if you like, or a moment, we call it, about an axis. And again, for equilibrium, static equilibrium, so if this body is not going to rotate in any sense, those couples, those moments, need to be balanced out in around each, well, in general first. So if we say the sum of all the moments has got to equal 0, and we can break that down into its orthogonal vector components, so we can say that in addition to these force equations here, we have the sum of all the moments about the x-axis are equal to 0, the sum of all the moments about the y-axis are equal to 0, and the sum of all the moments about the z-axis have got to equal 0 for there to be for this body to be in static equilibrium. So if we draw a rotated body in blue, the rotations about the x-axis, so if we rotate that body about the x-axis, we end up with it being something like this. So those rotations have given rise to a rotation about this x-axis. And rotations we quite often indicate by a double arrow on the axis, and that will give us a rotation about that axis, such as that. So that body will, under a non-balanced moment, will start to rotate. So in order to do that, we need to have a reaction, a moment reaction, which comes in the equal and opposite direction for that body not to rotate, as I've shown it there. And therefore, we say that in the x direction, the sum of all the moments has got to equal 0. So if we have a system of moments rotating that body, we need a system of reaction moments to resist that rotation. And just for completeness then, if we have that same body subject to rotations about its y-axis, we end up with a body which will rotate in this sense. So that will end up, I'm trying to show a rotation again with the double arrow around that axis. as the y-axis, and then the last one would be a rotation of that body about the z-axis. So if that body were not to be in static equilibrium, then we could get rotations which meant that that body ended up looking something like that. So it's had a rotation about that z-axis. Again, a double arrow to indicate that. So those are then the 6 three-dimensional vector equations which we need to establish to ensure that we have a body which is in static equilibrium. So most civil engineering structures are static structures. They're not either moving in any given direction or rotating about any given axis. And therefore, in order to calculate the forces and stresses and moments within those structures, we can rely on the fact that the equations of static equilibrium need to be satisfied, and we can use that to generate up to 6 equations. Okay. In terms of planar structures, so if we are considering, say, a beam which is existing in a plane, so it's a simply supported beam that might look or might be represented by a diagram, something like that. That beam doesn't have dimensions in the z axis, or similarly a plane truss, a planar truss we might consider, which might look something like that, again simply supported. So those types of structures, we consider them to exist just in one plane, in this, as we've drawn it here, the XY plane. And we'll come on to talk about sign conventions in structural analysis and why we might choose to use different ones in different situations. But for now then, if we're considering a structure that exists in a plane only, so it's not a three-dimensional structure, we only need to consider the forces in the x direction and the forces in the y direction. The forces in the z direction we don't need to consider for a plane frame, so we can get rid of, or we don't get rid of it so much as to say that all the forces, there are no forces in the z direction, so, and there are no reactions in the z direction, so they satisfy that principle of equilibrium in the sense that the sum of all the forces has got to equal 0. So we don't need to worry about this equation. Similarly, when we take moments, if we take moments in a plane, and we can take moments at any point in the plane because moments are a free vector, so the moments about any point in the plane are the same for the moments of all the forces or couples acting in plane will give rise to the same moment about any point on that plane. So we say we are considering the moments about the z-axis there. So we might consider this point here and take moments about that point there, or we might consider looking at a frame joint and considering moments about that joint in the frame. So these moments are about the z-axis. So we don't consider moments about the y-axis or the x-axis. So again, those equations we can do away with. The x moments and the y moments, and we only need to consider the moments in the z-axis. So for planar structures, which we're going to look at in this next series of videos, we will only need to consider forces in the x direction, the sum of equaling 0, the sum of forces in the y direction equaling 0, and the sum of moments about a point in the plane about the z-axis equaling 0. So those are our 3 equations of static equilibrium that we will use for the solution of plane frame statically determinate structures.